I'm recording now.
Okay.
Cool.
Thanks, Alan.
Cool beans. All right. Okay. So that I'm just gonna pull up my notes really quick on this. You guys can only see the whiteboard, right? Okay. So that's just. Okay. There we go. Okay. So I'm gonna go ahead and erase this entire thing. So we have, you have molecular geometry, and then you have electronic geometry. So molecular, electronic. So my workshop hasn't gone through this yet, so this might be new for the few students who are here. But anybody else, do you guys know what the difference between molecular and electronic geometry is? There is a difference, like a really tiny one, but it's really significant. What is it?
Hint, hint, it's in the name.
Would it be ionic versus, so ionic bonding versus molecular bonding?
Nope, we don't have anything to do with ions at this point. Not right now.
Good guess, though.
But yeah. Okay, so when you think about, when you see electronic, what do you guys think of electronic? Besides, obviously, technology, computers, and everything. But electronic, where does the word come from?
Electron.
Electrons, right? So what would be the difference between molecular geometry and electronic geometry?
One's with electrons and one's with molecules?
Kind of, yeah. So let me explain the difference. So molecular geometry is the 3D arrangement. So both of these are actually 3D arrangements, both of them. So the 3D arrangements of a compound. So both of these, so they both have this in common, compound. So the 3D arrangement is just the geometry. What makes them stand out, well, what makes them different is that the molecular geometry takes into account the electron, something called electron densities around them. Well, actually, the electronic, they both do take those into account. But this one actually takes into account the effect of lone pairs. And this one does not discriminate. Between atoms or lone pairs. Okay, so what do I mean by electron density? What I mean by electron density is just anything that might be around it can be either bonds or lone pairs, because that's where you can find electrons. Electron density, just wherever you can find electrons. And these can be either bonds between atoms, or bonds of, or lone pairs. Okay, does that make sense so far? Okay, let me actually show you an example. So let's take, for example, ammonia. We already talked a little bit about ammonia. Okay, so how many electron densities does ammonia have around it, around the central atom, which is nitrogen? It can be either bonds or lone pair, or just the lone pairs. So how many electron densities does ammonia have?
4.
4, right? So you have 1, 2, 3, 4. Okay, so the molecular geometry only takes into account how many electron densities you have around them and what kind of shape it makes. So if you guys take a look at your page, what page is this? I can't find my workbook. It's on the back cover of your workbook if you have it.
Are you talking about the
The
table?
little table thing?
Yes, the table.
Yeah,
The
it's right.
table.
So
It's right behind your hardcover periodic table on the back of your workbook. So just flip the page,
yeah,
and it'll be there.
it looks something like this.
So yeah, it does relate to VS EPR. It does relate to that. So this is what molecular geometry and electronic geometry relate to that. So molecular geometry, the thing about this one is that it takes into account how many atoms or how many lone pairs it has around it, and depending on how many it has, they'll have some sort of a specific molecular geometry. So let's take, for example, this case, ammonia. We already said we have 4 electron densities. 4 electron densities. So what is the molecular geometry if you have 4 electron densities around it? 1, 2, 3, 4. I see something in the chat. Hold on. Oh, okay.
Oh, it's just me. Don't mind it.
Oh yeah, you're fine. Okay, cool. So according to the table on the back, if you have 4 electron densities, what is the molecular geometry?
Well, it could be one of 3 things, right? Molecular could be tetrahedral, trigonal, pyramidal, or bent.
Okay, that's the electronic one, actually.
Are
It's
you
the
sure?
electronic-
Because it says molecular geometry on the table.
Okay, let me see. Okay, it's the electronic one. My bad. Yeah, this is actually electronic. My bad. Thank you. Thank you for fighting on that. Fight your professors if you know they're wrong. Just kidding. Okay,
We stand confident student.
We stand confident students. Exactly. Right. I mean, don't insult your peer leaders or your professors. Just be confident in what you know. Okay, so this is actually electronic geometry, and it only takes into account whether you have anything around it. So what is the electronic geometry for ammonium?
Tetrahedral.
Tetrahedral, right? So how do we know? So if we didn't have the table, how would you guys know? How would you guys figure out if it's tetrahedral? How would you guys figure this out just looking at it if you didn't have the table? In the exam, you're not going to have this table to help you. So what do you guys suggest? How do you guys think we can?
Tetra means 4.
Tetra means 4, yep. So tetra means 4. Can I send a picture of the table? It's in your workbook, Margot. Don't it's on the back of your workbook. So if you have it handy, you should be able to look at it. Okay, so tetrahedral, basically means you have 4 things around it, right? So that's the easiest way you can find out if you have a tetrahedral or not. And you might be able to look this up on Google too. Okay, so that was electronic geometry. But now so let's talk a little bit about molecular geometry. And there's something that, who was it that just corrected me, by the way? I need to bring up something that.
It was me.
It was Todd.
Todd, okay, I need the name. I don't know who's me. There are like 23 people here. They could be anybody. Okay. So we talked about electronic geometry. So let's, okay, wait, so far, do we have any questions so far? Do we need another example of electronic geometry before we move on to molecular?
Yes, please.
Okay, cool. So this is the electron geometry of a tetrahedral one. So let's take, for example, carbon dioxide. This is carbon dioxide. Okay. How many electron densities are around the central atom? Which one's the central atom?
Aren't there 4 around carbon?
Around carbon? No.
Okay, I think.
Okay.
Can you go over this, Corina?
Yes, you can take this one over real quick.
Okay, on the quicks. When we determine the densities around the central atom, or the, according to your table, right, the magic number, we're talking about different bonds. So double bonds in this case count as one area where you're bonding. Because yes, it's a double bond, you're right, there's technically 4 electrons in there, right? But those 4 electrons are still being shared with just oxygen. So it's technically just one bonding region instead of 2. So with that logic, how many bonding regions does the central atom have?
2.
I muted myself. We have 2, right? Because it only matters whether or not you have any atoms or any lone pairs around it, right? It doesn't matter how many bonds there is. It's either you can count either the atoms or the lone pairs, because this is the same electron density. This is the same electron density. So it doesn't matter how many number of bonds there is. Okay, so what is the electronic geometry of this one?
Well, it has to be linear.
Has to be linear, right? So if we didn't have, so this one's pretty simple. If we didn't have our workbook or our table to help us, to help guide us, it's easy to find out whether we have a linear geometry or not, right? Is it easy?
Yeah, because all the atoms are lined up.
Mm-hmm. They're just like in a line, right? It's fairly easy. Okay. You choose CH2O next. Oh, that's a nice one. Okay, I'll do that one. Okay. Okay, so I want you guys to help me with this one. Cause I know this one's in your homework, and I don't want to do your homework for you guys. Okay, CH2O. So which one is your central atom? Which one is going to be your central atom in CH2O?
Maybe carbon?
It'll be carbon, right? Carbon is your central atom. Okay. So how do we build CH2O? How many valence electrons do we need to use? How many valence electrons do we need to use here? See if you
How do we know which one is gonna be the one in the center?
So there are 2 ways. So it's either the least amount, and failing that, the least electronegative besides hydrogen, as long as it's not hydrogen. So which one is the least? So besides hydrogen, we have carbon and oxygen. Which one is the least electronegative?
Carbon.
Carbon, right? Carbon, right? So carbon is going to be our central atom. Okay.
Thank you.
No problem. So how are we gonna build this atom? How are we gonna build this? How do we build Lewis structures? Remember this. Yeah, Sophia's right. Hydrogen can never be the central atom. It can only be the terminal atom. It's its destiny forever and always.
So one hydrogen in each side, and then the oxygen can be in the top or the bottom.
Okay. All right. So how many so we built this skeleton. So how many valence electrons do we have available? We have 4 for carbon. We have 2 for each, 2 for both of the hydrogens. We have 6 for the oxygen. How many valence
12.
electrons do we? 12. How many have we used up so far by making the skeleton?
6.
6, right? So where are the other ones gonna go? On the oxygen, right? So okay. So which one? So how do we put them on the oxygen?
I would put a double bond to carbon and then put 2 lone pairs on oxygen.
Right, perfect. Okay. So now that we've built CH2O, right? Didn't do your homework so much for you guys. Okay, so how many electron densities do we have around CH2O?
3.
3. 1, 2, 3. What is the electronic geometry?
Trigonal planar.
Exactly, right? Trigonal, trig planar. I like to call it trig planar. So if you didn't have your exam, if you didn't have your table during the exam, obviously you can't have it on hand, but how would you guys know if it's trigonal planar?
Well, it's just what you said, Karina. We'd count the number of electron densities around the central atom.
What's another way you guys can figure that out? Because there's electronic geometry is trigonal planar. So triangle, you can think trigonal, triangle too. So if it's like a flat triangle, if it makes kind of like a flat triangle between all of these, you can think of it as that too.
Another thing I kind of want to bring up here is think about it in the 3D space, because obviously molecules aren't just 2D flat. So the trigonal planar, because if you remember that electrons are negatively charged, so and as well as like when other atoms are bonded to it, so from the central atom, you'll notice that the electron densities there, they'll kind of like negative and negative, they'll repel each other. So in a way, one example is called Trigonopyramidal, where yes, it does make that triangle shape, but there would sometimes be like a lone pair that would like push everything downward. So even though if we look at ammonia on the right, it is tetrahedral in terms of electron geometry, but in the shape of it, it looks like a pyramid, right? Because those lone pairs at the top are repelling the bonds that are to each of the hydrogen, so that's why it's making it kind of go downwards. So you got to think about it in a 3D setting, because that's how atoms are in a 3D space. So when you look at it like that, you got to remember like what's repelling what and like to what degree, and that's what the little table helps you out to do.
Right, and that actually brings me to what I wanted to talk about next, which I actually confused earlier. So that brings me to molecular geometry, which, like Alan was mentioning, Alan mentioned the lone pairs, they kind of push away the others, and this is what makes, for example, as he mentioned, it makes like kind of this pyramidal shape, but it's kind of like a 3D pyramidal shape. So this is because the lone pairs tend to push away others, the atoms, as far away from it as possible. So this is what the molecular geometry does, right? So lone pairs push other atoms and make different shapes. So earlier Todd actually was mentioning the molecular geometry, the possible molecular geometries you can have for tetrahedral electronic geometry. So electronic geometry stays the same. It only depends on how many you have around them. But molecular geometry depends on whether you have any lone pairs in there or not. So if you guys can look, so if you guys take a look at molecular geometry.
I already asked this in the chat. Sorry, Corina.
Oh yeah. Oh no.
But
You're good.
what is the name of the theory that tells us that electrons push themselves away from each other?
I think somebody mentioned it in the chat earlier. too.
Yeah, I'm just trying to see if anybody else put attention.
Did anybody catch that?
No?
It's VSEPR.
Yes,
Yeah.
ma'am. Woo.
You want to get super lazy? Some people call it the Vesper Theory. It's me. I'm some people.
I honestly remember it because you know how in that movie about the hamburgers raining, I don't remember the name, the part where they're like, oh, this is the fur. It kind of sounds like that. So
Like
Vesper.
Cloudy with a Chance of Meatballs.
Yeah, exactly.
That one. All right, cool. So you guys notice how the molecular geometry, so the molecular geometry is going to change if you have any lone pairs. So if you have the same amount, if you don't have any lone pairs, the electronic geometry and the molecular geometry are going to be exactly the same. But so see each. So for example, this is methane. What's the electronic geometry for this one?
What would be tetrahedral as well?
It would be tetrahedral too. And the molecular geometry for this one, since we don't have any lone pairs, is
Tetrahedral.
tetrahedral too. So what is the name of the molecular geometry for ammonia? Anybody want to chime in?
Trigonal pyramidal.
Trigonopyramidal. Right? So you guys notice the difference between the molecular and the electronic when you have a lone pair in there? Yes, no, maybe so.
I feel like you should go over like water. That's the most easiest and the most simple one.
Oh, that's a good one. Thank you. Yeah. I'm gonna go over that one. Okay, so I'm just gonna draw it for the sake of time. Just straight up. And I'm not gonna ask you to build it just like CH2OH. You guys already know how water looks like. Oh, two extra bonds in there. That shouldn't be. Okay, so what is the electronic geometry? Let's look at this one. What is the electronic geometry of water?
Isn't it tetrahedral?
Tetrahedral. Does anybody have any objections to that? Yes, no, maybe so. Okay, well, Todd's right. It's tetrahedral because remember, it's counts these two lone pairs. That's 2 electron densities, and then the hydrogens. That's 4, right? So that's tetrahedral. And I want you guys to remember that because remember these lone pairs are not there because they look pretty, right? Okay, so what is the molecular geometry of this one?
Wouldn't it be bent?
It's bent, right? So this one is fairly easy. it might be a little bit easier to find out what the molecular geometry is. As you can see, just looking at what kind of shape it does, like it looks bent, you guys can figure out, oh, this is a bent molecular geometry. Does this make sense to you guys? Everybody good with this?
I feel now that we kind of I feel like now you guys have gotten the grasp of this. Corina, do you want to like go over polarity since we have water there already?
Oh yeah, actually, I guess nobody's. I guess you guys have no more questions. So let's go over with polarity for a second. So
For those of you guys that have been here with us for a while, does anybody remember what we said earlier about polarity? Corina
did
brought it
mention
up,
polarity.
actually.
oh yeah, actually, I did tell you guys this would come up again later. So if you guys have been here for module, what was it?
I think it was
12.
module 11.
It was 12. It was 12.
Was it 12?
It was 12 because we were talking about electronegativity, right? Okay. So I'm actually going to leave these, all of these structures because these are really, really good structures to talk about polarity. Okay, so for those of you who've stuck here for a while, I'm sure it's most of you, remember what I said about electronegativity? So what's electronegativity? What's the trend for electronegativity?
You mentioned something about dipoles, right?
I mentioned something about dipoles. So how did those dipoles come to be? How do those come into existence? Why do those dipoles come into existence?
Hint, hint. Think of a magnet.
They carry like an unequal charge. Negative and positive.
Okay. So why is there a negative and a positive charge? So there's a positive and then there's a negative. So what causes that to happen?
Corina just gave you guys a giant hint.
Come on, guys. We went over this about 2 hours ago.
Okay, let's backtrack. What is electronegativity? Anybody?
Don't leave us hanging like Dorothy Explorer, guys.
The pull of the electrons towards the nucleus.
Could you say that a little bit louder?
The pull of the electrons towards the nucleus. Is that what you said?
Yeah.
It is pull of electrons, but not towards the nucleus. Pull of electrons. So you're super close. You're really close. It does have to do with pulling electrons, but pulling electrons where? What are those? Where are those electrons? What are those electrons doing? In what? Pull of electrons in what? In
a compound, right?
Right.
Like how
it has
it's
to do with a compound, right? So, okay, you guys are on the right track. So pulling electrons in the compound, how do you make compounds? What do you need two atoms to do to make a compound? Two or more.
You need two elements.
Two or more of them. What do they do to make a compound?
Well, if it's a covalent compound, they share electrons.
I heard somebody say the answer earlier, but they're kind of quiet.
Did ionic? Oh.
Okay, let me show you guys the answer that I heard from one of you guys. Bond. And shout out to my quiet dude. I don't know who it is, but I can barely hear you, but I did hear you say bond. So shout out to you, man. Okay, so it's the pull of electrons in a bond. So electronegativity is just how strongly an element is able to pull the electrons towards itself in a bond, especially in a covalent bond. So yeah, covalent bond. So you guys were in the right track. Pull of electrons in a covalent bond. So this is the trend. It goes from right to left, sorry, from left to right, and from up, down to up. So the higher up you are and the more to the right you are, the more electronegative you are, without counting the noble gases. So in the case of water, which is more electronegative in comparison? Hydrogen or oxygen?
Oxygen.
Oxygen.
Oxygen, right? So the electrons are going this way. So what are these arrows I'm drawing? So overall, the net direction that the electrons are going, if you know about a little bit about vectors, you know that if they are opposite and equal magnitude, they'll cancel. So the net vector that is made is going which way? Does what I'm saying make sense, guys? Goes this way, right? It's going, this is going upwards. So what is this? What are these arrows I just drew? What are these supposed to be?
Aren't those the dipole arrows?
Yep, those are dipoles, right? So this is a dipole arrow. So if it's
oh no, sorry. So
go ahead, Sophia.
I was gonna say, because you know how the arrow has like a little cross thing at the end, right? The way I like to think of it, this isn't how it works, okay? The way I like to think of it is the arrow is pointing towards whatever's more negative, and the little cross is just reminding you where the positive side would be. That's not how it works, but like that's how I remember it.
So it can help you guys to understand it too. So the more negative pole is oxygen. So here on the top, and the more positive pole is where?
Well, it has to be hydrogen.
Yeah, by the hydrogens. Okay. So what happens here is if
Excuse me, Karina.
Yes,
Excuse me just a minute. What is the symbol you're writing before the positive and the negative? The things you just wrote. What is that?
That's sigma.
Okay.
That's actually a delta. So this is how we usually represent these. This is a way we can represent the kind of the poles of the dipoles, because even though this is not like this is not exactly a this is not an ion, right? These are not charged. These are not charged compounds. Water is not a charged compound, right? But it's polar because there's kind of more of a concentration of negative of electrons over here. That kind of makes it a little bit kind of negative. So this is how we represent them. These are just symbols to represent it.
Yeah, so what the symbol is saying is, it's not like Na plus, right? Because Na plus is definitely positive. These symbols are saying they're kind of positive and kind of negative. They're not
they're partially, yes. Mm-hmm.
Yeah, exactly.
Right. They're like partial charges. So if this dipole is not canceled in any way, so remember I told you guys that dipole arrows are kind of like vectors, and if these arrows are not canceled in any way, so remember vectors, if you guys are familiar with physics, you might know that vectors, if they're opposite if they're in the opposite direction and they have the same magnitude, they cancel each other out. But if you don't have anything canceling out this dipole, for example, then this is going to make it polar. It's going to be a polar molecule, right? You have polar bonds, right? So these right here are your polar bonds. Polar bonds, because you have, because you have the electrons going to the more electronegative atom. Does that make sense, guys?
Yes.
Right. So just to recap, electronegativity makes us can create dipoles. So that makes polar bonds. And if there's nothing canceling out this dipole arrow, if there's nothing canceling out the dipole arrows, then you have a polar molecule. You can have polar bonds without being a polar molecule. Do you guys know that? Okay. So how about we look at an example where we do have polar bonds, but we don't have a polar molecule. So polar bonds does not a polar molecule make. So let's look at methane right next to it, right next to water. So which one is more electronegative here, carbon or hydrogen?
Carbon.
Carbon, right? Okay, super easy. Basically, one, it has a different terminal elements, or two, the central atom has lone pairs. Exactly right. That's a really good way to look at it. If you have different terminal elements, you're most likely to have a polar bond in there, or you have a dipole in there. So that's a way you can find out, at least if you have any polar bonds, or if the molecule is polar. If you have the lone pairs, it's a good possibility that your whole molecule is polar. So thank you, Jimena, for sharing that. Okay, so back to methane. So we know that carbon is more electronegative than the hydrogens, right? So the dipole arrows would be pointing towards the carbon. And carbon is pulling with this all of the electrons with the same strength, right? So what did we mention about dipole arrows? That they're like what? Or they are. They are. What are they?
You're talking about vectors earlier.
Right, they're like vectors. So the dipoles are like vectors. So think of that. Think of the vectors. If they have equal magnitude directions, what happens to those vectors?
They will cancel.
They will cancel, right? So do these dipoles, these vectors cancel out?
Yes.
Yes, right? These cancel out, these cancel out, these cancel out. So even though you definitely do have polar bonds, because you know that carbon is more electronegative than hydrogen, that makes them polar bonds. Overall, is the molecule itself overall polar or non-polar?
It would be non-polar.
Non-polar, exactly right. Right, because even though you do have polar bonds, the vectors are canceling out, you have a non-polar molecule. Okay. So let's look at, are you guys good, or do you guys need a few more examples of polarity? Yes.
One more example.
Okay, sure. All right, let's look at ammonia down here. So which one is more electronegative? Hydrogen or nitrogen?
Nitrogen.
Nitrogen. So here are the dipoles pointing this way, right? Okay. So we know that, but that this is how we know we have polar bonds, because we have nitrogen is more electronegative. Is it overall a polar molecule? Are the vectors canceling out?
How do we know which way the arrows are turning?
So remember we
pointing-
said that, oh, sorry,
Okay.
Karina, go ahead.
Sorry, Sophia, keep going.
Remember we said that the arrow is pointing towards the most electronegative element, and that's going to be determined by your trends on the periodic table. And then the little line, that's not how it works, but the little line is reminding you what side is a little bit more positive. Okay, so that's a good way to remember it. It's always going to point towards the most electronegative element.
All right.
Thank you.
So let's see. Overall, is this polar or non-polar?
Polar.
Polar, right? Polar molecule. So this is fairly easy. This was fairly easy. What about this one? Oh, do you guys need one more, or you guys got the hang of it? But we do one more example.
I feel do an example where I guess the vectors technically aren't canceling each other out, but they're like pointing in way opposite directions, like carbon dioxide.
Oh yeah, that's a good one. I
'Cause
was
rem-
gonna do a monoatomic one. Sorry, a diatomic one, but that one's actually better.
You could remember for polarity, think of it like a magnet where you have a general positive end and a general negative end. So all the electronegativity in the molecule has to go in like a generally one direction. So this example is kind of showing you like why it would be technically nonpolar.
Okay. What about this one? Which ones are the most electronegative elements or element?
Oxygen.
Carbon or oxygen?
Oxygen.
Oxygen.
Oxygen, right? So which way would the dipoles be pointing? Towards those, right? So if there's dipole, so that if there's these if we can draw these vectors, we know that there's a polar bond. But does a polar bond a polar molecule make? In this case?
No, it's nonpolar.
It's non-polar, right? Non-polar.
Why? I love
Why
this
is that?
question.
To me, it's like the two vectors that cancel each other out.
Exactly. These vectors are canceling each other out because the electrons are being pulled with the same strength by both of the oxygens. So one on the other, on one side, one on the other side. And it's kind of like tug of war. It's also a way your workbook shows it. That's how I sometimes like to think about it. So they're pulling the same strength on the carbon. Nobody's winning. Ultimately, it's a non-polar molecule because all the electrons are going opposite ways, same strength. It makes it non-polar. Okay. How do you guys feel about this one? I think these have been, how do you guys feel about polarity? So this whole thing was, sorry, polarity. This whole thing was polarity. So do you guys have any other questions, concerns, complaints?
Any leftover questions? Anything at all about polarity or anything that we've covered today? Any requests for the last 15 minutes?
I was going to talk a little bit about hybridization.
Yeah, I was gonna say,
Yeah, that was my
Just
request.
kidding.
Yeah.
That's the last thing, really.
Okay. All right. Thank you, Jimena. If I'll take a look at the picture Jimena just sent in a moment, because I really want to look at it, and I really love the how she's been giving to the review.
I can
Thank you,
attest
Jimena.
it's a good picture. It's a visual of what Jimena shared with us earlier. 10 out of 10 would recommend downloading.
Yes, you got it, Jimena. Somebody hire Jimena for peer leading next semester. All right. Okay. So last topic of the day is hybridization. Okay. Alan, do you want to talk a little bit about this? Or, I mean, I was going to talk a little bit about hybridization, but I think I've talked a lot.
Yeah, I could go over it. So, let me. Can you like stop sharing so I can like?
Oh yeah.
There we go. So, what it is, if you remember back from bonding, the orbitals, like you know how the different shapes are p and s orbitals, they combine into almost one orbital. And if you look at your kind of example, you look at the table where it shows the hybridization number, like of the central atom, shows like sp and like or spd, stuff like that. That's just how we're combining the orbitals, right? So let's take so the way you would a little cheat sheet I would look at it is it's kind of like thinking of like, you know, like how many electron groups are connected to the central atom, or like what's its sort of hybridization. So a little shortcut, like to think of it, let's look at methane, for example. So we have C and like CH4s. So if you remember, carbon have what orbitals does carbon have?
Think back to electron configuration.
So it has 1s, 2s, and 2p.
Exactly. So for now, kind of showing demonstration, it has the like it has sorry yes it has like the p orbital, right? And then hydrogens have the s's since it's the only thing. So we would have an sp sort of hybridization for the central atom. And the way we would number it, a little shortcut I would do is I would look at the central atom and count the number of bonds it has. So we see that has 1, 2, 3, 4, and and once you count up to 4, I would do this. I would write sp and then subtract 1 from 4, so it'd be sp3, for example. And the reason for this is if we look at the little, like, there's like an example where we do like boxes. So let me quickly look for that example. I know it's on here somewhere. Yeah, here. So if, let's say, here, I'm trying to look for that methane example. Here. So if we remember, so hydrogen has a s orbital, so it's the 1s being the little arrow. But then carbon has the 2p, right? And how many electrons are in the 2p orbital for carbon, I mean?
This is 2.
Yeah, 2, right? So actually, let me put the s, because technically it has 4 valence electrons. So let me do this. So carbon has the 2s filled up, and then 2 in the 2p. So whenever they bond, because here we have hydrogen and then here we have our carbon, the orbitals kind of like mush together, they combine. So what happens is we have to combine all these boxes now. So we would kind of, so let's do one, let me scroll down. So here we have, sorry about that. So here are one giant box where we have 1, 2, 3, 4, 5. And what we do when we combine them all, we have to configure the electrons as it would be, as we would do it normally. So like going upwards and then putting them into pairs. So here we have 1, 2, 3, 4, 5 electrons. So we would go 1, 2, 3, 4, and then 5, right? And so if I'm missing something, please let me know, guys. Or if
I think there should be 4 boxes.
Yeah,
Yeah, because
Yeah, if I'm actually, yeah. Sorry for confusing you guys. Yeah, because we're only looking at the outer orbitals, because we're looking at carbon's 2p orbital, and then the 2s. Yeah. So sorry about that, guys. So since these orbitals come together in a sense, we would have our 4 boxes, and since they're the 2s and 2p, this would be 2sp. And so we would have our 4 boxes aligned. Sorry if it's kind of crooked. And as again, we would line them up as we were doing normal electron configuration. So we would go 1, 2, 3, and 4. So yes, we have 4 in total. And then from here, what you would do I don't know. I don't remember why. I just remember this was the shortcut. You would like discount one electron and make that as the exponent. So this will become like, since we have 2s because it's on the 2s and 2p orbital, it become 2sp3. And
three of those.
yeah, and like this would be your like this is the hybridization, like the combination of those orbitals. So even though it's kind of complicated, this is why I like using the shortcut where once I count up to 4 bonds of the central atom, I subtract 1 and just go sp3. But say, for example, you have more than that. So that's when you start including the d orbitals. So let's see, what's a good example here? Let's see, let me clear all this. Let's see, Sophia and Gorian, do you guys have like a example?
I don't have an example, but can I add something real quick?
Yeah, go ahead.
When it comes to hybridization, you remember how many electrons can an s orbital hold and how many electrons can a p orbital hold? Anybody?
Well, S can hold 2 and a P can hold 6.
6, right? So when it comes to hybridization, think of it as the shells can now hold half as many electrons. So with that logic, in hybridization, how many electrons can S hold and how many electrons can P hold?
Well, it would be 1 for S and 3 for P.
Yeah, exactly. And, you know, technically, if we were to move on to D, it would be 5, right? But in Gen Chem, we're not going to go beyond P, so you don't have to worry about that. It'll always be...
You can go a little bit.
You can?
Yeah.
There are some examples with D, like SP3D. So, yeah.
I don't remember taking those, but yeah, okay.
Oh, that's for like, for example, PCl5.
Yeah.
Okay.
Yeah, so this is just showing this.
So yeah, so it'll always be half as many electrons as it can usually hold. So if D can usually hold 10, then in hybridization, it'll hold 5. Does that make sense?
Yeah, so let me show you guys an example of what Sophia was mentioning. So I was telling that one of the examples was, for example, PCl5. So phosphorus does not follow the octet rule, right? This is one of the examples of phosphorus not following the octet rule. So if you guys were to build PCl5, how many bonds would you have to phosphorus on phosphorus?
I think you would have 5
Fair
because
enough.
you'd have the 5 chlorines around it.
Yeah, exactly.
Yeah. Right. So yeah, 2, 3, 4, 5, 6, 7, 8. And if you guys take Gen Chem 2, you guys are gonna have a faster way to do it. Okay, so so electrons, like for example, PCl5, they have this. There's a theory that says they are capable of hypervalency. So hypervalency basically means they're able to use d orbitals. So they're able to use some of the d orbitals to be able to make more than 4 bonds that, for example, you would in sp3 compounds, like that have that sp3 hybridization. So so what happens is that this is the configuration of phosphorus. So this is 3s2, 3p3. Okay, so remember what we mentioned. So remember what we said about the possible values of L? What are the possible values of L if you have n equals 3?
0, 1, and 2.
0, 1, and 2. So what subshells do these correspond to? 0, 1, and 2.
SP and D.
SP and D. So if you have n equals 3, in theory, you should be able to use those empty d orbitals to your benefit, and that's exactly what phosphorus does. So because it has n equals 3, and all the possible values of L are 0, 1, and 2. So if you have, so here, you know how earlier that Alan was showing you guys how sp3 worked, that we took one of these electrons and we put it on the next, on one of the p orbitals. So we made sp3 hybrid orbitals. You guys remember, right? Okay. So here instead, we're going to take this electron all the way up to this d orbital, 3d. So we're going to put it over here, and using all of these orbitals, these are kept unused. This is what creates what we call sp3d hybrid orbitals. So now we have 1, 2, 3, 4, 5 orbitals and 5 electrons at our disposal, which phosphorus is able to use to make 5 bonds to each of the chlorines. Does that make sense? I know this is, I like to explain this because I didn't understand hybridization myself when I was a student. But if you guys kind of want the shortcut to this too, well, one way I like to do it, I think, did you mention how like you do counting, Alan?
Yeah. So like going back to methane, so let me draw this next to it, where I would count the number of bonds at the central atom up to 4. So in this case, we have 1, 2, 3, 4. So because you always start with S and then P, so here would be SP. Since I count up to 4 bonds, I subtract 1 to make it 3. But here in this case, for like what's it called, phosphorus tetrachloride, so I would count up to 4 as usual. So it'll be 1, 2, 3, 4. So that'll be sp3, and then anything after 4 would be D. And then we would have this hybridization, right? So say for example, this would probably most likely not happen, but let me quickly erase this. Say I have like a fifth bond, right, to whatever, something, right? Using the shortcut again, because I would count anything after 4 as my D's. So counting again, so being 1, 2, 3, 4, being sp3. Yeah, 1, 2, 3, 4. And then seeing there's 5, 6. Since there's 2 more after the 4th one, it'll be D2. So it'll be sp3 D2. So that's like the little shortcut way of counting it. Like you wouldn't count. Oh, go ahead, Sophia.
I have a similar trick, except instead of counting them, I literally label them with letters. So this would be like S and then P. This is P1, and then this is P2, this is P3, and this would be D, and then D1, and then D2. And so then I just write the biggest number one. So it'd be S, P3, and then D2. And that's what we have here.
Honestly, that would probably work better than my method.
Okay.
So right. Is everyone kind of clear on that? Is there anyone that's confused or have any issues? All right, so I'm just gonna stop sharing since no one has questions.
Okay.
So it's officially 5 o'clock. I think we're gonna call it quits. Alan, if you just want to stop recording.